Hello everyone, I welcome you to the third problem solving session of NPTEL course Graph Theory. I hope my voice is audible and my screen is visible. Are you?
Yes, ma'am.
Okay. So let's start. So before starting today's session, there were two questions that were left in middle in the last session. So first I'll quickly go through those two questions. So first question was on finding the diameter of hypercube, which is Qn. So Qn is a specific type of graph. It is also called a hypercube. It is a graph which has 2 raised to the power n vertices, and so it can be represented by a graph whose vertices are subsets of this set of first n natural numbers. And any subset of first n natural number is a vertex of this graph, and any two subsets are connected by an edge if and only if the difference of two sets is a singleton element. So in on right hand side you can see I have drawn q as in sample drawn q2 and q3. So there are four subsets of first two natural numbers, and we see empty set is connected with the singleton set, and so this singleton element 2 is connected with 1 2, but empty set is not connected with the complete set 1 2 because difference of these two set is not 1. So we see this is q2. Similarly, we can draw q3. So in q3, so first of all we'll list down all the vertices. Vertices will be the subset of first three natural numbers, and then two subsets will be joined by an edge if the difference between those two subsets is 1. So now so the question is to find diameter of Qn for general n. So for my claim is that diameter of Qn will be n. So first of all, recall what was diameter. Diameter was basically maximum of duv, where uv were in the vertices, uv were the vertices, and duv was the length of shortest path between u and v. So in this problem we'll show that diameter of Qn is n, that is maximum of length of shortest path between any two vertices is n. So this I have divided into two cases. So first case is, so basically we have to to find the diameter, we have to compute the length of shortest path between any two distinct vertices. So first case is, so any two subsets are any subset is any subset of the set 1 to n is a vertex of the graph. So first case is we are picking two subsets in which one is contained in another. So suppose first we want to calculate DAB, where A is contained in B. So if A is contained in B, A will look like A will have, suppose A has some K elements, and since A is contained in B, B will have all these elements of A plus some additional elements, and I am saying that it has some additional elements L. So AK plus 1 till AL. Now in this graph, in Qn, if we want to find the shortest path between A and B, this will be if you want to find any path between A and B, it will be as follow. Because we know in this graph any two subsets are connected if they differ by just one element. So we see if we want to go from A1 to AK to A1 to AK plus L, we can go via this path. First edge will be from A to A union AK plus 1. Then second edge will be from the vertex A union AK plus 1 to A union AK plus 1 to AK plus 2, and so on. At each edge, at each step we are adding just one element, because two subset has an edge only if they differ by one element. And we see, so number of edges here will be L. One one number of edges will be L, one edge for each additional element. So for case 1 we have shown that if A is contained in B, then then the shortest path between A and B will be of length which is the difference of the elements of two sets. Is case 1 clear to everyone? Is there any doubt in case 1?
No, ma'am.
Okay. So, and in particular, if we look at the worst case scenario, so in this graph we can see the worst case scenario is the empty set and the complete set, and difference of these two set is n. So we see that the shortest path between empty set and the complete set of n element has length n. So if so, hence, and since diameter is maximum of all these shortest path, this diameter has to be greater than equal to n. So for case 1 we have proved. Now we look at the general two vertices. Now for general two vertices, we'll show that the shortest path between general two subsets is less than equal to n. And if we are able to show it, then we will be done. So suppose this next case. So first case was A is contained in B. Second case is A is not contained in B, and neither B is contained in A. So since this shortest path is a symmetric relation, so we know that if A is contained in B or B is contained in A, the shortest path is just the difference of the bigger set from the smaller set. Now Case 2 is when we have two general subsets, none of them is contained in another. So how do we go about it? We'll use case 1 for this. So we'll first look at a path from, so we know that A, B both are contained in A union B, and A union B is the smallest subset which contains both A and B. So first we'll go from A to A union B, and then we'll go from A union B to B. And from case 1 we know that distance shortest path between A to A union B has elements of A union B, number of elements in A union B minus number of elements in A. And similarly, shortest path between A union B to B has number of elements in A union B minus number of elements in B. And now if we want to find the shortest path between AB, we know that shortest path will be less than equal to length of this path plus length of this path. And length of this path is A union B minus A, and length of this the other path was A union B minus B. So if you look at this Venn diagram, you will see that first thing for shortest path between A to A union B is this region A, and shortest path from between length of shortest path between B to A union B is this shaded region C, number of elements in shaded region C, and this is nothing but order of A union B minus order of A intersection B. So you can, A union B is A plus B plus C, and what we want to calculate is A plus C, which is A union B minus A intersection B. And this difference will always be, because A intersection B is a non-negative number, this will always be less than equal to order of A union B. And order of A union B, since A union B is a subset of 1 to n, we see that this order is less than n. So we have shown that if we pick any two general vertices of Qn, which will be two general subsets of Qn, the shortest path between them has length less than equal to n. And we have also given an example of two vertices whose shortest path has length n. Therefore we see that diameter Qn is exactly equal to n. So is this question clear to everyone? Is the first problem clear?
Yes, ma'am.
Okay.
Yes, ma'am. Clear, ma'am.
Okay. So the other problem that were left from the last lecture was this. So so the other problem was this, that if G is a regular graph of diameter 3, then we had to show that G complement will have diameter 2. So we almost solved this problem last time, but like there was just last minute last few things left. So first of all, to solve this first of all, to show this, we'll be using a result in the lectures. There was a result in lectures that if diameter of G is greater than equal to 3, then diameter of complement of graph will be less than equal to 3. Therefore, since in this question diameter is 3, so clearly it is equal to 3, so it is clearly greater than equal to 3. Therefore we get that diameter of G bar will be less than equal to 3. But now we have to show that if we have an additional condition that G is regular, then this diameter of complement of graph should be equal to 2 provided diameter of G is 3. So we need to show this. So we are proving it by contradiction. Suppose if possible diameter of G bar is not equal to 2. And we know that diameter of G bar is less than equal to 3. Therefore and diameter of G bar cannot be equal to 1. Because if diameter G bar is equal to 1, we are basically saying that there is an edge between any two vertices. But since G will have some edges, because G is a regular graph of diameter 3. Then G bar cannot be a complete graph, and therefore diameter of G bar cannot be 1. And we are assuming that diameter of G bar is not equal to 2. Therefore we are just left with one possibility, that diameter G bar is equal to 3. So now if diameter G bar is equal to 3, so now we have that, now we want to arrive at some contradiction. So we have that diameter G is also 3 and diameter G bar is equal to 3 and G is regular, then we are trying to arrive at some contradiction. So if diameter G is equal to 3 and diameter G bar is equal to 3, we can find four distinct vertices V, W, X, Y and G, such that shortest path between V and W is 3. Length of shortest path between V and W is 3 in G, and shortest path between X and Y in G bar is also 3. So now we want to look at all the possible relations these four vertices can have within each other. So now first of all, this is clear, right? That if diameter of V and W is 3, then V and W cannot have any common vertex in G. And similarly, X and Y cannot have any common vertex in 3. Now, and since diameter of VW is 3, VW cannot be an edge in G. Therefore, VW will be an edge in G bar, because that's the definition of G bar. All the edges which are not present in G will be present in G bar, and vice versa. So we see that VW will be an edge in G bar, and X diameter of shortest path between X and Y has length 3. So in G bar, so XY cannot be an edge in G bar. Therefore they will be an edge in G. So we have got one relation between these relation between these vertices, but now since we know that they won't have any common neighbors in the respective set, using that also we can find further relation. First of all, since V and W will have no common neighbors in G, because the shortest path between them is 3. And if V and W have a common neighbor, say V prime, then we will be able to find a path of length 2. But we know that the shortest path between them is 3. Therefore, VW cannot have any common neighbors in G. Moreover, XY cannot have any common neighbors in G bar. So we see that either XV belongs to G or YV belongs to G. If these two edges are not in G, if these two edges are not in G, if these two edges are not in G, then we see that these two edges will be in G bar, and X and Y will have a common neighbor in G bar, which cannot be true because distance of shortest path between X and Y has length 3. Therefore, we see that either one of these edges should be there in G. So suppose XV is that edge in G. Now if XV is that edge in G, and similarly we can do this for W also. So we know that either XW or YW will be in G, but further, since XV is in G, YV cannot be in G, because then YV cannot be in G because YV cannot be in G because then we will have common neighbors. We will sorry, X and Y will have common neighbors. Therefore we see that these are the only possible relation. These X, Y, V, W have these possible relations in G and G bar. Now once they have these only possible relation, our next claim is that our next claim is that if we sum up the degree of V and W in G, it will not be equal to the sum of degree of X and Y in G. And if we show this claim, we are done, because since G is regular, these should be equal. But if we are able to show that these LHS is not equal to RHS, we have arrived at a contradiction and our earlier assumption was wrong. So now what is remaining to show that given that XYVW have only these possible relation, that LHS cannot be equal to RHS. So first of all, these were the 4 vertices, but this graph obviously have more vertices than these. Suppose S is the subset of vertices which has all the vertices of G except these 4 vertices, and M is the number of edges going from XY to S in G, and N is number of edges from VW to S in G. So yeah, now if M is the number of edges from basically M is the number of edges from the set XY to S, then what will be in G, then what will be the degree of X in G plus degree of Y in G? So it will be M, because all these edges, it will be M because these edges are going from X to Y, and it will have plus 2 also, because we can see X is connected to Y and V in G. So this 2 is coming from XY and XV, and this 2 is coming from YX. This is coming from YW plus YW and YX. So we see that this is M plus 4. And similarly, if we do the similar calculation for G bar, this we see that N, there are the degree of this is N, plus we'll have 1 for, because Vx is also connected, so this one is contributed by edge Vx, and this one is contributed by edge YW. So we see that degree of X and Y in G is M plus 4, and degree of W and V in G is N plus 2. So is it clear up till now, this problem?
Yes, ma'am.
Okay. And then we just have to show that this M, so now then we just have to show that these two quantities are not equal, because that is what we were trying to prove. So now if we take any vertex in this graph G except these 4 vertices X, Y, W, we have these relation that first there exists at least one edge from U to XY in G. This is because X and Y can't have common neighbor in G bar. Therefore, if we pick up any vertex, at least one of we pick any vertex, it has to be connected to either X or Y. And other thing to be noticed is that there exists at most one edge from U to VW in G, and this is because VW cannot have common neighbor in G bar, can't have common neighbor in G bar. So if we pick up any vertex, there have to exist at least one edge from U to XY, and there can exist at most one edge from U to VW. Therefore, we see that M is greater than equal to N. And if M is greater than equal to N, we see that M plus 4 is strictly greater than N plus 2. So M plus, which implies that M plus 4 is not equal to N plus 2, and hence our claim is proved, and hence we see that G can't be regular, but we have that G is regular, so we have arrived at a contradiction. So our assumption was wrong, and diameter G bar has to be 2. So this was this code. So is this problem clear? Okay, I know there will like it, this was bit tricky problem, so I'll be uploading notes, so you like if you have any problem in these steps, you can post in the forum. So now we'll move on to today's topic. So week 3 was about trees and finding minimal spanning trees. So what is a tree? So tree is a connected graph with no cycle. By connected graph, we mean that any two vertices can be connected by a path, and any connected graph with no cycle is a tree. So you can see this is an example of a tree. This is a connected graph, plus we have no cycles present here. So this is a tree. And forest is a graph whose every component is tree. And then there are so we and then we had some we showed some result in class that a tree on n vertices will have n minus 1 edges, and so from this we can deduce that forest on n vertices and k connected component will have n minus k edges. And by leaf we meant to say a vertex which is of degree 1 in tree. So you can see all the vertices which are labeled red are leaves because they have degree 1. But this one is also a leaf. But these two vertices are not leaves because their degree is greater than 1. And then we had this problem that, so the first thing that we want to show is that G is a tree if and only if there exists a unique path between any two vertices. So let's show this. Suppose G is a tree. How do we show that there exists a unique path between any two vertices? Any suggestion? We assume that G is a tree. And now we want to show that there exists a unique path between any two vertices.
Method of contradiction, because
Yeah.
trees does not contain a cycle.
Yeah. Good. Yes, you are right. So what he is saying that if we pick any two, so we'll show that there exists a unique path by between any two vertices by a contradiction. So suppose there does not exist a unique path between some vertices, say V and W. So that means we have a path P1 from V to W, which is going from V1, VK, W, and then we have a path P2 from V, W1, WK prime, W. So suppose if we have this, so but tree is a connected graph with no cycle. So given two path, what cycle we are getting? So how are we arriving at contradiction? What is the so we assume that there does not exist a unique path between V and W. we get two paths. We get two paths P1 and P2 from W. So what is the cycle?
PV1,
Yes.
VK, W,
Yeah.
WK up to W1.
Yeah. So we see that we have a cycle, is a cycle, but T has no cycle, but G has no cycle. So we arrived at contradiction. Hence a contradiction. And what about converse? Conversely, so we suppose we have a unique path between any two vertices, then we have to show that G is a tree. So what we have to what two things we have to show, what two things we have to show that a graph is a tree? What is the definition, like what two things are needed to show that graph is a tree?
Its graph is connected
Yeah.
and acyclic.
Yes. Connected plus acyclic. And that is pretty connectedness is pretty obvious, because if there exists a unique path between any two vertices, there exists a path between any two vertices, and we see that it is connected. And it is acyclic using the similar argument, because if a graph, if it is not acyclic, if we'll have a cycle, suppose we have a cycle, say v1 v2 vk w and v1, we can, yes, suppose we have a cycle like this, then we can break this cycle. Say suppose we have a cycle like this from v1 v2, we can break the cycle in middle, and we'll get two different paths between v1 and vk. Therefore we see that if there exists a unique path between any two vertices, the graph has to be acyclic, and therefore this condition is true that G is a tree if and only if there exists unique path between any two vertices. Okay. So this was simple. Now, now, now what we know, now what we want to do, we want to find the spanning tree. So first of all, what is a spanning tree? A spanning tree is a subgraph of G which is a tree and has all the vertices. And we can see that every connected graph has a spanning tree. So suppose this is your connected graph. The edges which are colored with red or which are colored with green give you a spanning tree, because so if you see the red ones, it is a tree because it is connected plus has no cycle. Moreover, it has all the vertices. Therefore we see that the red one is a spanning tree, and for the similar reason green one is also a spanning tree. So every connected graph has a spanning tree, and this example show that the spanning tree need not be unique. Now, once we know what is a spanning tree, what is a minimum spanning tree? A minimum spanning tree is a spanning tree of it's weighted graph. By weighted we mean that every edge has been assigned some cost or some weight. A spanning tree of minimum cost will be the minimum spanning tree. So now let's solve some questions. So first I want to look at the second question. Suppose this is was also in your practice assignment. Suppose G has a unique heaviest edge E. So this is a true or false question. You have to suppose we are given a graph G which has unique heaviest edge E. Then the statement say that then E can't be a part of any minimal spanning tree. So is it true or false? What do you think? By unique heaviest edge E we mean, so we have some graph G every edge is every edge is assigned some weight. If every, in this graph every edge has been assigned some weight, and the highest weight belongs to one edge. So the statement is saying that if G has a unique heaviest edge E, if E is the heaviest edge, then E can't be part of any minimal spanning tree. So is it true or false? What do you think?
Means it is a cycle is true, I think. G as a cycle. If it is in a cycle,
If it is okay, that is part one. But if it is not in a cycle, then what do you think? Is it true or false? So we second statement is false, because you can look like even so if you just look at some tree is also a graph, and tree will have some unique, suppose we are taking this as our G. So this is a graph which is a tree, and its heaviest edge is 5. So and you see that it spanning tree is this tree, spanning tree is also this graph itself. So so we see that the minimum spanning tree of this G has the heaviest edge. So this statement 2 is not always true. So this is false. We can't say that any minimal spanning tree won't have the heaviest edge. Now somebody was saying that first part is that suppose this heaviest edge is contained in some cycle. Suppose we have this. Suppose this heaviest edge is contained in some cycle like this. Then can we say that E cannot be a part of any minimal spanning tree? Then is it true?
we can remove the edge, no? Yes,
Yes.
madam.
Yes. Yes. In this particular example only you can see that we can so if we label this vertices A, B, C, D, E. So we can have a minimal spanning tree A, B, C, E, which does not have the heaviest edge. But still we have to prove this. So we are claiming that this is true. Now we want to prove this, that suppose G has a cycle with unique heaviest edge. Sorry, G so G has a unique heaviest edge contained in a cycle. Then claim is that E cannot be a part of minimal spanning tree. So we'll prove this by contradiction only. So suppose E is a part of some minimal spanning tree T. Minimal spanning tree T. Then T minus E. What can you say about T minus E? Will this graph be connected or disconnected? So we are trying to prove this by contradiction. So we are assuming that G has a unique heaviest edge E, and this edge E is contained in some cycle. Now we want to prove that it cannot be a part of any minimal spanning tree. We are trying to prove this by contradiction. So we are assuming that there is a minimal spanning tree T which has this edge E. So first point is that what about the graph T minus E? What do you think? Will it be always connected or disconnected? Can we say something about that? Suppose E is equal to VW edge is EVW. So suppose if we have any tree T, so this is a tree because it has no cycle. Now if we remove an edge E from T such that none of its endpoints are leaves. I mean, suppose this is the edge I am removing. So you see, our graph is becoming disconnected. So is it always true that if we remove a edge from T, if we remove an edge from a tree, and that edge is appearing in sometimes middle, it appearing in middle, that is, none of the endpoints of this edge is a leaf, then can we always say that T minus E will become disconnected? So we can see that this T minus E for this kind of edge will become disconnected, and it will have two components. And has two components, C1, C2, say. And now if we compute the minimum cost edge in this cut, we'll get an edge whose weight will be less than weight of E, because E was the highest weight edge, and T minus E union that edge F, that is the minimum cost edge, will be a spanning tree whose weight is less than of T. But we assume that T is the minimal spanning tree, therefore we get a contradiction. And why this edge will be different from E? Because see, if we so like in this graph, so we see that this was the highest weight edge. It was contained in some cycle this. So what we are doing, we are saying that suppose we remove this edge. Now if we remove this edge, okay, if we remove this edge, we see that we are left with this. VW. And now see, in this case, this graph hasn't become disconnected because W is a leaf. So if I take my S to be W and S prime to be the rest of the vertices, A, B, V1, V2. Then what will be the minimum cost edge? So if this is my partition, what will be my minimum cost edge? So if we want to compute the minimum cost edge, what do? We write W here, A, B, V1, V2 here. And we write, so this is the partition and we do this. So if you want to find the A, V1, V2, this is V and this is V1. Yes. So A V1 V2 W. Sorry. A sorry. So my partition is A, what this is B, A B V1 V2 W, and if I want to compute my minimal cost edge, S is W, A B V1 V2. So we see that we don't have any edge between, this is blank, WB is blank, WV2 is 3 and WV1 is 4. So we can choose this. So we can choose, so our minimal spanning tree, our minimal spanning tree was, our initial minimal spanning tree was A B V A B BV2 V2W and V1W. Now, and this was containing the heaviest edge. So now the new tree is, we are subtracting the edge V1W and adding V1 V2. So we see that if we have a heaviest weight edge which is contained in some cycle, we can remove that edge and add an additional edge from that cycle to get a spanning tree of lower weight. Therefore our first statement is true, that if the heaviest edge is contained in some cycle, then it cannot be a part of any minimal spanning tree. So is this first part clear?
Yes, ma'am.
Okay. So now, yeah. So now we have the second part is to now the second question is to find the minimal spanning tree using Kruskal's algorithm. So we have to find the minimal spanning tree using Kruskal's algorithm. So what does the algorithm say? Algorithm say, first we take our set to be singletons. So we have all these vertices A, B. So we take the set till F, A, B, C, D, E, F. So we are trying to find a minimal spanning tree in this graph using Kruskal algorithm. So what does the algorithm say? For our initial set is this, and whenever order of V is greater, so let's call this W. Whenever order of W is greater than 1, V and T is here empty. So whenever order of W is greater than 1, we pick up the edge with smallest weight. So in this graph, what is the edge with smallest weight? So we are trying to construct a minimal spanning tree. So first step is to pick an edge with the smallest weight.
One AB, ma'am.
Yes, smallest weight. So the edge is AB, and so then we see that if A and B are contained in different set, then we accept that edge. But if they are, pick an edge with smallest weight. If pick an edge with smallest weight, suppose this edge is some V1 V2, and if V1 V2 are in different sets in W, our W becomes, we merge, so we, if suppose V1 is in set some S1, V2 is in S2, we merge those sets, S1 union S2, and rests remain same. So now at first stage our W was this. So now what will be our W? since our first edge is AB, so we merge AB and then rest are singleton. C, D, E, F. And tree has AB. AB is the first edge. Now once we have find this, now we repeat the step. Now besides AB, what is the smallest weight edge now? So which edge should be
B.
now? Yes. So now we
B.
pick BE. 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 And now at second stage so this was TAB. Now at second stage BE. B and E are also contained in different sets, so we merge those sets. A, B, E. And now we are left with C, D, F. And new tree becomes AB, BE. Now after AB and BE, what is the smallest weight edge? BF, right? And BF are also contained in two different sets. Therefore, we accept that edge. So now it becomes A, B, E, F, C, D. And this T becomes A, B, D, E, E, F. BF, sorry.
Ma'am, AE is having
AE.
lowest.
Yes, yes, AE.
Yes.
So first was AB, then it was BE. Now the next edge was AE. But can we accept that edge AE? Okay. Okay, before, okay, sorry. So yeah, you are right. After BE, the next smallest edge is AE. Oh shit. Oh, sorry, this was, yeah. So okay, this was not the edge. Yeah. Next edge was AE. So can we, so according to algorithm, can we accept the edge AE? Okay. So there was this edge also. This has weight 4, this has 2. So see, now at the next step, the edge AE with weight 3 is there, but we cannot accept the edge AE because AE are contained in same step. So we reject the edge AE and then we move on to the next possible shortest weight. And next possible shortest weight is BF. Now BF, B and F are contained in different sets. Therefore we accept BF. So is this step clear to everyone?
Yes, ma'am. Yes, ma'am. Clear, ma'am.
AB, BE, then we have BF. And we are rejecting AE. So now this was BF. So now next, what edge should we pick next? What edge should be the next? So we have picked weight 1, weight 2, weight 3 edge was rejected. Now the next weight was 4. Now we see that two more edges have weight 4, but we cannot choose any of these two edges because so we cannot choose AF. So reject AF and reject FE because we see A and F are contained in the same set and FE is also contained in the same set. So we reject both these edges. So what is the next possibility? Next possibility is BD. Now B is contained in the first set and D is contained in the second set. So we accept BD. So now our W become A, B, E, F. We are and D and C. And in our tree we have an additional edge. And now what's the next edge? Now we see that after 4, the next edge is CD, weight 5. And C and D are lying in the different component. Therefore, we accept lying in the same component. Therefore, we accept CD. Now, our W becomes A, B, C, D, E, F. And we accept CD. And now, since the order of W has become 1, we stop our algorithm. Because our algorithm has to be like, we have to keep repeating it whenever the order of W was 1. So, we see in the end, this is the minimal spanning tree. So, is this algorithm fine for everybody? How we are...
Yes, ma'am.
Yeah. Okay. So, yeah. Hello. Is there any question?
Ma'am, but here it's not necessary to continue from the last endpoint. That's it, ma'am.
Yeah. So yeah, we weren't in this case we weren't continuing from the last endpoint. We were always looking for the edge with minimum weight.
Okay, ma'am. Okay. Thank you, ma'am.
Minimum weight, like so whenever we are adding some edge, we are removing that. Besides that, so whatever edges we have accepted or rejected beforehand, beside those edges we are looking for the edge with minimum weight. Here endpoint is not important. Endpoint will be
Okay.
important in the Prim's algorithm, which we'll be doing like next.
Okay, ma'am. Thank you, ma'am. Thank you.
Okay. So now, so yeah. So now we have this graph and so we'll see Prim's algorithm will be computing will be like in the next question we'll be finding minimal spanning tree using Prim's algorithm and Prim's algorithm uses this step first of all, that if we are given a cut of vertices. By a cut of vertices we mean that we have a set of vertices V and we are writing it as a disjoint union of S union S prime. So given a cut of vertices, we are trying to find the minimum cost edge in that cut. So by minimum cost edge we mean that, so yeah. So yeah, so minimum cost edge in a cut. So as I have defined previously, what is a cut? We are basically dividing the set of vertices into two disjoint sets. So now so minimum cost edge in the cut will be the minimum of all the edges with whose one vertex lie in S and the other vertex lie in S dash. We are considering all those vertices whose one endpoint is in S and the other endpoint in S prime, and we are looking at the weight of those vertices and we are looking at the weight of those edges, and the edge with the minimum weight is the minimum cost edge in the cut. So in this following diagram you can see in this following graph we have our cut in this manner. So first cut is ABE and second cut is DC. So we have these two cuts. And now we want to find the minimum cost edge. So how do we find the minimum cost edge? So ABE is the first cut and CD is the second cut. So now we want to look at all the possible edges whose one edge is lying in the set S and others edge whose one vertex is lying in set X and other vertex is lying in this set S bar or S complement. So we can see this. So what are the possible edges from ABE to CD? So if this is the first cut and this is the second cut, we only have three edges. First is AD, which has weight 2. The other edge which is possible is BC, which has weight 1. And the another edge is ED, which has weight 3. So minimum cost is, so we see that BC has the minimum weight. So minimum cost edge in this cut will be BC. So now once we know what is a minimum cost edge in a cut.
But,
Yes, yeah, is there a question?
I mean, that previous diagram, is it,
Yeah.
is it necessary to select the cuts like A, B, E and C and D?
No, it's not.
Otherwise,
No, this is the minimum cost edge for the following cut.
okay, ma'am.
It's
We can take also like A, B, S is equal to set A and B and S dash is equal to set D, C. Like that also we can take.
Yes. Yeah. So yeah, one is S and other is the S complement. So basically, the cut is that the union should come out to be the whole vertices and they should not have a common element. So cut. So,
Okay, ma'am.
so it should be a disjoint union. So if
Okay,
you are
ma'am.
so it should be a cut AB and DCE is also a valid cut.
Okay, ma'am. Thank you, ma'am.
So now we see, so now like in this question you see, in this question we have two in this we have two cuts and now we are trying to find the minimum cost edge. So first cut is this. So first cut is this. So what are the A, B, C, D? First cut is this. A, B, C, D. And the second cut is E, F, G, H, I. So we want to find the minimum cost edge in this cut. So basically we have to look at all those edges whose one vertex is lying in S and other vertex is lying in S prime. So we'll make a table kind of thing to record all these things. So first part A is this. So since first cut is this A, B, C, D, so whenever there is a cut, we write one cut in a horizontal. So we write one set in the horizontal row and other in the vertical row. And now by GA we mean if edge GA is present, the weight of that edge. So in this particular case, so first of all E. So what were the values? So E we can see is connected with D and C, and D and C are in the other cut. So we see that EA has no edge, EC will have weight 2 and ED will have weight 1. Now similarly we'll go for other vertices. So we see that F is adjacent to, now if you look at the vertex F, it is adjacent to three vertices G, H, D. But FG and FH, we are not considering those edges because their vertices are both lying in the set S prime. But we want that one vertex should lie in S and other in S prime. So the FD is the only edge that we want to record. So if we look at FD, this is this and rest all are black. Now similarly if we do for G, okay, so G, so we see G, we cannot take F, we cannot take I because they are green. We can only take GC, which has weight 3. And for H, so we see H is not adjacent to any vertex in the other set. So all will be blank. And I, for I we have that IA is there with this 15 and this. So you see in this cut what is the minimum cost edge?
ED.
ED. So ED is 1. So this was the first cut. Now similarly we have this other cut. Yeah. So we have this other cut. First is A, C, E, G. And the other cut is B, D, F, H, I. So in this example, maybe like by inspection or see like without drawing the table, like if you can see. So can you tell me what will be the minimum cost edge for this partition, for this cut? Maybe you can draw it in your notes also.
ED.
Which one you are saying?
Same ED only.
ED only. Yes. Yes, you are right. So see, ED will be the only edge, but because one vertex is in E, one vertex is in S, and other vertex in prime, and it has weight 1, and none of the edges has weight less than 1. So we see in the second part also the cut edge will come out to be ED. But this so in this particular case cut edge is coming out to be same, but this is not a case in general that whatever cut you take you always end up in the right with the same answer. In this only case you are getting. Okay. So now we understand what minimum cost edge is. Let's do the Prim's algorithm. Let's run the Prim's algorithm to find the minimum spanning tree. So now if we want to use the Prim's algorithm, first of all, for using Prim's algorithm we should always know what vertex we are starting with. So here our S is A and T is empty, and while, so what we do that while order T is less than n minus 1, where n is the number of vertex. So we know any spanning tree will have n minus 1 edges. So while T is less than n minus 1, what we have to do is we have to keep on adding minimum cut edge of S bar. So now let's do this. So this is the algorithm. So like with this example we see. So what we have to do, we are initially starting with A. So our S is A. And so the complement has all the remaining vertices B, C, D, E, F, G, H. So in first iteration, what is the edge that has to be added? So we have A, so we see only two of these will be non-blank. First A, B, and okay, we have I also. So total number of vertices are 1, 2, 3, 4, 5, 6, 7, 8, 9. So basically we'll run this algorithm till we get 8 edges. So we see that in first step our we are starting with A. So our first step S is A and all the rest vertices are belonging to the complement. So and A in this, see, A is connected to just B and I. So what is the first, in first iteration, what is the edge with minimum weight? What is the minimum cost edge for S equal to A and S bar equal to B, C, D, rest of the vertices? What is the minimum word?
7.
Yes, 7. So AB is our first vertex. So I'll also write a number. The red number is depicting the stage at which it is being added. So okay, let's take black only. So T has one edge AB. So now our S becomes AB, and S bar is the rest of the edges, C, D, E, F, G, H. So in the second iteration, the edge that has to be added is for this new cut, S bar. So basically A and B are in the same set, and then we have the complement. So what do you think will be the next edge?
C. BC.
Yes, because yeah, BC will be the next edge. So we see AB, and we are looking at we are looking at all the edges which are starting from which have one endpoint A or B and rest other vertices, and there are just two such edges, BC and AI, and BC has the least weight, so the next edge will be BC. So this is the next edge. So now T has two elements. Now at this stage S becomes ABC. Now at third stage S becomes ABC, and S bar is the rest of vertices, which is D, E, F, G, H, I. So what is the next vertex? What will be the next vertex? What will be the next edge? So for that we want to find the minimum cost edge for this partition. S equal to ABC, and this is D, E, F, G, H, I. So what is the next edge? Okay. So paste. So our yeah. So our first edge was AB, then it was BC. Now we have to find the minimum cut edge for this partition ABC, and this is D, E, F, G, H, I. So now if we see this, so we have AI, so all these are blank and this is just AI. Now if we look at for B, these are all blank, and for C we have options. For C we have CE, which is 2, CD, which is 4, and CG, which is 3. So what is the next edge?
CE.
Yeah. So at third step we are adding CE. Now this is happening at third step. Now our S becomes ABCE. So now we have to compute the minimum cost edge of this cut. ABCE, D, F, G, H, I. So now this will be same. This is 15. For B, this is all blank. For C, now for 4 and 3. And for E, we have ED, which is 1. That's it. So now what is the next iteration? What is the next edge? Clearly
ED.
it is ED. So we see it is ED. Now next step S. Now our S becomes A, B, C, D, E. Now our S becomes this. So now we compute the minimum cut edge for this cut. So A, B, C, D, E. F, G, H, I. So now what is the next edge? So if we fill this table for A, we have just I, which is 15.
CG is the next.
Huh? Sorry, yeah.
CG, CG.
CG. You're saying CG. Yes, that's right. Next we have CG. Because in this cut, now the cut, so these are the vertices in the cut. Yeah. Now the next cut has these. Now G is also included in our S. Now our S become A, B, C. So this is added at fifth step. Now our S becomes A, B, C, D, E, G. So what is the next vertex? So we one. So now this is the cut. So now next edge should have one vertex in the blue, the one which is circled with blue, and other from the remaining one. So what will be the next edge?
GF.
GF. Yeah. So now we see this. This is next edge is GF. And now this is also included in our S. Now the next edge will be
GI.
GI. Yeah. So now this is also included. And the next vertex is, now the next edge will be IH, right?
Yes. No.
Yeah. And if we now count the number of edges, if we count the number of edges 1, 2, 3, 4, 5, 6, 7, 8, and there are 9 vertices. So we have found our minimal spanning tree, and we exactly precisely know which edge is added at which iteration. So is this algorithm clear for everybody? I can repeat any step if it is not clear. Is it clear for everybody how to find minimum spanning tree using Prim's algorithm?
Yes, ma'am. Clear, ma'am.
Okay.
Ma'am, but one doubt, ma'am.
Yes, yeah.
Using Kruskal's algorithm and Runprim's algorithm,
Yeah.
whether we get same minimal spanning tree or not.
Oh, so you might not get same minimal spanning tree, but the if you calculate the weights will come out to be same.
Okay, ma'am. Okay, ma'am.
Weights of both the trees will come out to be same.
Okay, ma'am. Which algorithm is efficient, ma'am? Comparison.
This is more efficient because in a way, because so in Kruskal's algorithm at every stage we are looking at the weight of every edge, but now in Prim's algorithm the number of edges become comparatively less because we are
Oh,
looking at the
yes.
cut edge.
Okay,
So
ma'am. Okay.
so,
Like
so
iterative steps. Okay.
yeah, yes, because see this is relatively a small graph. Suppose if you have a graph with lot many edges, then applying Kruskal algorithm will be difficult, right?
Yes,
Because
ma'am. Yes, ma'am.
then if you start with some edge using if it is a large enough graph, then this algorithm is more efficient.
Okay, ma'am. Thank you.
Okay. Yeah. So now the next question is, consider a reversed Kruskal algorithm for computing a minimal spanning tree. So now they are giving us another alternating method, which is reversed Kruskal algorithm. So how is that working? We set t to be all the edges in graph, all the edges, and now we are considering edges from largest to smallest cost. So basically in this, like in this algorithm, what we are we'll look at this particular example later. So what is the algorithm is that uh, look at the highest weight edge. Look at the weight with look at the edge with highest weight, and if that edge is contained in some cycle, remove it. So this is a reverse Kruskal algorithm. So did you understand the algorithm? So what we are doing, we are looking at a graph. We are looking now, instead of looking the edge with the smallest weight, we are looking at the edge with the largest weight. And if that particular edge is contained, if it is contained in some cycle, then we are removing it. So now the question is, assume now the question is that, assuming all the edge costs are distinct, does this new algorithm correctly compute a minimal spanning tree? So what do you think? If we keep on doing this, will we end up with a minimal spanning tree or not? So let's look at an example. Suppose we have this graph only. A, B, C, D, E. And suppose we also are assuming that all edges costs are distinct. So suppose I'm like randomly 3, 4, 5, 6, 7. So this 4 is for this edge and this is this. So what is the, so let's try to find a minimal spanning tree using this. First let's try to use this algorithm to find a tree, and let's see if we'll end up with a minimal spanning tree or not. Then we'll see if it is true or not. So what is this algorithm saying? Look at the edge with highest weight. So what is the, so in this diagram, what is the edge with highest weight? AD, right? And this algorithm is saying that if this highest weight edge is contained in some cycle, then remove that edge. So is AD contained in some cycle in this graph? What do you think?
Yes, ma'am. In ABD.
Yeah, ABDA is a cycle. So according to the algorithm, first step is remove AD. Okay. Now after AD, so now once we have removed AD, okay, this was our original graph. Now, so okay, I am coloring removed edge with red. So if an edge is red, assume that it's removed. Okay, remove AD, edge is with red. So now what is the
CD.
Yeah.
CD, ma'am. Now.
Now CD is the highest weight and it is also contained in some cycle. So now the next step is to remove CD. Okay, after CD, ED, right?
ED. Yes, ma'am.
And is ED contained in a cycle?
EBD.
EBD. Yes. You have to make sure that like the cycle that you removing, like you are not counting the edges which are removed in the cycle. So EBD is right. Next is remove ED. Now what is next? Next is AE. Can we remove AE?
Yes, ABE cycle.
Okay, yeah. ABE is a cycle, right? So we can remove AE also. Great. Now, the next is EB. Can we remove EB?
No, the graph will be disconnected.
Okay, so we can't remove EB. So that means our algorithm, okay, now see, like now the remaining graph, so the remaining graph has no cycles, so we have to stop. So that means this is the minimal spanning tree. Sorry, this is the spanning tree that we are getting, and we can see that it is also minimal because it has 1 2 3 4 edges. So we see that for this particular example, we are getting for this particular example, we are indeed getting a minimal spanning tree using this algorithm. But do you think will it be always be true? And if it is always be true, can you think of a reason why this is true? We have done a similar like so hint is in the one of the questions that we have done today, the very first question that we did today. So we showed earlier today that we showed that if an edge has unique highest weight and is contained in a cycle, then that edge can never be in part of some, then that edge E can't be in any minimal spanning tree. We showed this, right? And in this algorithm we see what we are doing. We are basically, since all the edges have different distinct weight, so at each stage the highest weight edge is unique, and if that highest weight edge is unique and is contained in a cycle, then we are removing it. Therefore there is no harm in removing that edge, because we have already shown that any such edge can never be a part of minimal spanning tree. So do you see why this algorithm will, so this algorithm, if we use this algorithm, then why we will end up with minimal spanning tree always. So is it clear? Is this question clear to
Ma'am.
it? Yeah,
Yes.
hello?
Yes, ma'am. Clear.
Okay. Okay. So now there's another question. So first of all, we are given a connected graph with n vertices and m edges and positive edge cost. So basically all edges have positive cost. And we also are assuming that all these costs are uh, distinct. Okay, we don't need to assume this. Yeah, so we are looking at a connected graph with n vertices and m edges and positive edge cost, and let T be a spanning tree. We define the bottleneck edge of T to be the edge of T with greatest cost. So what is the bottleneck edge? So suppose we are given so first of all, what is the bottleneck edge of a tree T? Suppose you are given a graph G and T is a spanning tree for that particular graph. Bottleneck edge refers to the edge with the highest weight in that tree. And a spanning tree of G is called a minimal bottleneck spanning tree if there is no other spanning tree with a cheaper bottleneck edge. So do you understand? So first of all, what is a bottleneck edge of a tree, and what is a minimal bottleneck spanning tree? So let's understand this definition with an example. Suppose you are given this graph. G, then bottleneck. So this is a graph G, and T prime, which is AD, BE, AB, and BC. So we can see that this red is a spanning tree of this graph. Now the question so red is the spanning tree. So bottle edge neck. Yeah. So bottle edge neck will be the, so we have these four edges. Bottleneck edge is the edge with the highest weight in this tree. So we see that
B.
BE is the
B.
bottleneck edge for this tree. So this is what is a bottleneck edge, and we call this spanning tree bottleneck spanning tree if we cannot find another spanning tree whose bottleneck edge has a lower weight. So this is T prime. Do you think is this T? So I have written it. So this T prime you can see is the bottleneck edge spanning tree, because the highest weight edge is 4, and you cannot have any other spanning tree which does not have a, which you cannot have any other spanning tree which has a bottleneck, or sorry, which has bottleneck edge of lower weight. Is this fine? Why T prime is a bottleneck edge spanning tree? So any spanning tree of this graph G will have 4 edges. Any spanning tree of this graph will have 4 edges, and you see since 2 of the edges have weight 4, so since 2 of these edges have weight 4 and one edge is weight 5, so we see that any spanning tree will have either an edge of weight 4 or weight 5. So we see that T prime is indeed a bottleneck edge spanning tree. Now this was T prime. Now we are taking T. T is this different tree which is blue, which is, yeah. So T is AD, DE, AB, and BC. So what do you think? Is this T, first of all, what is the bottleneck edge of this T? Of this spanning tree? Bottleneck edge of this spanning tree.
D. DE.
D.
DE. Yes. DE. So now from the definition, is this spanning tree minimum bottleneck spanning tree?
No,
Why?
because we can draw the previous T dash T prime spanning tree.
Yes, because we can have a spanning tree which has a bottleneck edge of lower weight. So we see that this is not a bottleneck edge line. Now the next question is that, is this, so we see that T prime is a bottleneck edge spanning tree. So in this graph, is this T prime a minimum spanning tree also? Is this T prime the minimum spanning tree for this graph? So one,
Yes,
yes. Why? Hello?
is less edges.
Yes, because we can see that it has 4 edges which has the least weight in its which has the least weight in this graph. So we cannot have any other collection of 4 edges which have more weights. So we see that is this T prime is minimum spanning tree also. So in this particular case, we can see that our bottleneck, so this T prime is a bottleneck edge spanning tree, which is also coming out to be a minimum spanning tree. So this question is asking you this only. So is this always true that a bottleneck spanning tree, is it always true that a bottleneck spanning tree is a minimum spanning tree? So what do you think? First of all, can you find in this graph, So if in this graph, any other bottleneck spanning tree which is not a minimal spanning tree, if you can do that, then this statement is false. Then we can clearly write the answer is no. So in this following graph, is there a bottleneck spanning tree which is not a minimal spanning tree? This is the, I'm just making it bit bigger. Same graph. So can you find a bottleneck spanning tree in this graph which is not a minimal spanning tree? So I am telling you that this graph has a minimal bottleneck spanning tree, which is not a minimal spanning tree. This graph has a bottleneck spanning tree which is minimum bottleneck spanning tree which is not a minimal spanning tree. Can you find that?
D, A, B, E,
Wait.
and C.
What can you say? D E.
Path. D, A, path. D, A, B, E, D. No, no, no. No. This can't be. D, A, B, E, D, C. D, A, B, E, C.
Huh. So what are you saying? So which one you are saying? Yeah.
Path. D, A, B, E, C.
Sorry. D A
E,
B
E,
C.
no. Okay. Or E, C or C, E. Same. I was saying C, E, C. Okay.
C E.
C, N.
But this is a minimal spanning tree only, na? Right? One,
No,
two,
no.
three,
I
four.
was saying B to E and E to C.
Okay. Yeah, that is right. Yeah, that is right. Good. Good. So see, yeah, you are saying this one, right? This one you are saying, right? So you see
Yes,
that,
yes.
so this is a bottleneck minimum spanning tree because the highest bottleneck edge is 4 and there cannot be any other spanning tree with lower bottleneck edge. But this T prime that we have already constructed earlier has lower weight than this new T double prime. So we see that any bottleneck spanning tree, any minimal bottleneck spanning tree, can need not be a minimum spanning tree. So this was the question. Okay. So is this question clear to everybody? And his example and his example is also clear to everybody. So he has found a tree which is a minimal bottleneck spanning tree, but not a minimal spanning tree. Okay.
Ma'am,
Yeah. Yeah.
how you are saying that it is not a minimal spanning tree, ma'am?
Okay.
Once
Yeah.
again, please explain.
Yes. So yeah. So if you look at the why this is not a minimal spanning tree. So see, in this the edges are AB, BE, EC, and AD. And what are the corresponding weights? AB has weight 2, BE has weight 4, EC has weight 4, and AD has weight 4. So if you add these weights, you are getting 4, 8, 10. Yes. If you add this weight, you are getting total weight to be 11. But earlier only we have constructed this T prime which has total weight 10. So since it has a higher weight than T prime, this cannot be a minimal spanning tree.
Okay, ma'am. Okay, ma'am.
Right? Okay. But
Yes, ma'am.
this is a bottleneck spanning tree because the bottleneck edge is 4 here also. And any spanning tree has to have an edge of weight greater than equal to 4. So this question was basically you have to give an example of a bottleneck spanning tree which is not a minimum spanning tree, and we have given that. Now is it clear?
Clear, ma'am.
Okay. Now, oh, not this grade. This is not graded assignment 3, I guess. Wait. Oh. Oh. Okay. Practice assignment. So now, like I am done. Sorry. So I am done with the practice problems for today. So now we have three. Now we have two options. Either we can. So this was question from practice. Either we can discuss. We can quickly discuss the questions from practice from the graded assignment 1 and 2 which you have already submitted. If you have any doubt, we can discuss those questions, or we can look at the like there's only one or we can look at the practice assignment 3. So what, which one will you prefer? Or if you have any questions from, if you have any general questions, then you can ask like from the lectures or something.
Then from the assignment 2
From
of graded assignment. Yes, ma'am.
yes,
Second
okay.
question of graded assignment 2, ma'am.
Okay, yeah. Wait, let me present my screen. Yeah, for grade. Oh, okay. Okay. Wait, sorry. Oh, yeah. Sure. Okay, so you are asking for which question? So is the screen visible now? Yeah.
No, ma'am. Screen is not visible. Yes, ma'am. Now it's visible.
Okay. Yeah. So which one you are saying? Week 2.
Yes, ma'am. Week assignment 2 of second question of assignment 2.
Okay. Graded 1.
Graded 2, ma'am.
Okay. Yes, I'm putting that. Yes. This. So your this k-dimensional cube.
Yes, ma'am. Hypercube QK.
Yes. So a k-dimensional hypercube QK is a simple graph whose vertices are k tuples with entries in 0, 1, and whose edges are the k tuples that differ in exactly one position. Then is Q3 isomorphic to the so you have to show that if this Q3 is isomorphic to this bipartite graph, right?
Yes, ma'am.
Okay. Yeah. So first let me.
Ma'am, Q3 will have three sets, no? It will be bipartite.
Why Q3 will have 3 sets? Yes. What are you saying?
It will never, it can be bipartite,
Yes.
Q3.
Huh. Yeah. Yes. Like yeah. Q3 is bipartite. Yeah. So we'll see that. Wait. Okay. So now I think it is visible, right? My writing screen. Yeah. Yeah.
Yes, ma'am.
So okay. So first we have to check if is Q3 bipartite. So I gave a bit different definition of Q3, but like do you see, like, why do you get the definition of Q3? Are you fine with the definition of Q3? So what? So see, so we had this our Q3 was this. Our Q3 was this, right?
Yes, ma'am. Yes.
So so basically, so what they are saying is that they are taking it to be 0 1 entry. So in this case, this is this 0 0 1 0 0 0 1 and 1 0 0. So they are taking this as Q3 0 1 1 1 1 0 and 101, and this is 1. So so their definition is this. So instead of looking at a subsets, they are looking at the sequences of so if it is Q3, we are looking at sequences of zeros and 1, and they are connected if they differ in exactly one entry. So now we want to see if this graph is bipartite or not. So first of all we know that, so we showed that a graph is bipartite if and only if it has no odd cycles. And in a way to prove that, how we did so if given a graph and if you want to see if it is bipartite or not, what do? You pick some vertex, say 0 0 0. Now you put all the vertices, all those vertices whose shortest distance path is odd in one set and whose shortest distance path is even in the other set. So in this case, if you pick 0 0 0, so you see, so with 0 0 0, I'm picking up, writing all those vertices which have whose shortest path is of even distance. So you see 0 1 1 and 0 0 0, it has shortest path of length 2. So I can take this. So and similarly 1 1 0 and 1 0 1. And now if I take this vertex as, now all the other vertices other than these, all the other vertices other than these are at odd distance from this vertex 0 0, are at shortest path has odd distance. So if you do write down all the other vertices 0 1 and 1 0 0. Now if you see, now if you want to see, so like now make all these connections that are present. So 0 0 is connected with these three vertices, 0 1 1 is connected with 0 1 0 0 0 1 and 1 1 1. 1 1 0 is connected with this 1 0 0 and the ones which are differing by just one entry, this, and 1 0 1 is connected with, as you can see, with this one and this one. So you see, this is coming out to be bipartite, right?
Yes, ma'am. Yes, ma'am. Now it's clear, ma'am.
Now it's clear? Okay.
Yes, ma'am.
Any other question from graded assignment 1 or 2? Or any, like, up till week 3, if there are any doubts, you can ask. Okay, so okay, I'll quickly go over assignment 2 then. Yeah. Okay, so what? So for the first question, what was the answer? Which of these graphs are isomorphic? G1, G2, among G1, G2, G3.
This
Which
was solved, no, means in the online session. No, no,
No, this wasn't solved in the online session.
but we answered it. I think G1, G2, G1 and G2.
Yeah, G1 and G2 were coming out to be isomorphic, because you can see that this will also be a by part. So now, okay, so that is fine. But can you say why G3 is not isomorphic to G2? Why
We can't
G3?
do the one to one relation or
Yeah, yeah.
vertex to vertex relation.
Or like, or you see, or like, or there's an there so there's one more quick way to see it. Like, if you, so showing that there is no function might showing that there is no function between, there is no one correspondence function might be difficult. So what to show that if two graphs are not isomorphic, you try to look at some property which is present in one graph but not present in another. So you see that G2 is a bipartite graph. So if these two graphs were isomorphic, this should be bipartite. So do you think G3 is bipartite? A graph is bipartite if and only if it has no odd cycles. So do you think G3 is bipartite?
Not that is the reason I found that it is not isomorphic, but I can't give the reason now.
Okay, yeah. So basically, if you have to show that it is not bipartite, you have to give me an odd cycle. If you are able to look at find some odd cycle in G3, then this graph will not be bipartite, right? So can you
Yeah.
find a odd cycle in this graph?
3, 4, 5.
This one will be an odd cycle, right? Going
Yeah.
from theta, alpha, beta, gamma, delta.
Yes.
1, 2, 3, 4. So this graph has an odd cycle. Therefore, this is not bipartite, and therefore G2 and G3 cannot be isomorphic. So is this clear to everyone? The first problem?
Yes, ma'am.
Okay. Now second problem we have discussed right now. What, okay. So what was the diameter of this graph?
2, ma'am. 2.
2. Okay. Why it was 2? So you can see all the vertices, all the,
Max
yeah,
maximum distance
yeah,
is from any vertex to the other vertex is 2, ma'am.
yes, yeah. That's why it has diameter 2. Good. Now, what about this? Is this graph bipartite?
Yes, ma'am.
Yes. Okay. So also see, if you have to find out if a graph is bipartite or not, there is a trick. Like there's like trick. So you try, like you want to see if there are bipartitions or not. So first of all, first thing is you check if you can visibly see any odd cycle. If you can't see any, if you can't find, if you can see an odd cycle, then you can directly say that this graph is not bipartite. But somehow, suppose you are not able to find a odd cycle, then you try to construct those bipartition. So you fix a vertex A, then from A, list, so construct two sets. From, if first set is the set of all vertices, set of all the vertices whose shortest distance from A is even. So put A and those even distance vertices in one set, and put B, put B and put, and the other set is the set of vertices which has odd distance. And then see if there are any edges between those odd vertices and even vertices. So if there are no edges, then you would have constructed a bipartition. So you would have proved that it is a bipartite graph. But if you can find there is an edge between them, then you will see that using that edge you will be able to construct a cycle. So in this case this will come out to be bipartite. So what you will do, your first set is A. So now you look at the vertices which are whose shortest distance from A is odd. So what all vertices whose shortest distance from A is even. So what all vertices will be that? You are trying to construct a bipartition. So what all vertices have even shortest distance from A?
K, F,
K,
H,
K, right? K, H,
F,
F, yes. K, H, F, and C also, right?
C, C, yes, ma'am, C.
So now you'll able to show that A, K, H, F, A, K, H, F, and C. They are forming one bipartition, and the other vertices will be forming one bipartition. So now next problem was, are trees bipartite? Okay. So are trees bipartite?
Yes.
Yes. Why? Why are trees like? So you are saying why are trees bipartite?
There will be no cycles, ma'am.
Yes. Good.
First.
Yeah. Yes, there will be no odd cycles, and this is the necessary and sufficient condition for bipartite graph, that a graph should have no cycles, no odd cycles. Sorry. Good. Now next question was, next we solved in the class a graph has 20 vertices, then the maximum null. In the last session we solved it and it was coming out to be 100. Okay, so what about the seventh problem? So given G a bipartite graph and bipartition of this graph are U and V respectively, what is the relationship between them? So is it always okay? So first of all, let's go one by one. We are given that G is a bipartite graph. So is it always true that in the bipartition, number of vertices in U should be equal to number of vertices in V?
Not necessary.
Not necessary. Yeah, because we can look at KMN, complete bipartite graphs only. So first thing is not true. Now second thing is, sum of degree of vertices in U should be equal to sum of degree of vertices in V. Is this true?
Yes.
Yes, this is true, because we know in a bipartite graph, every edge has one endpoint in U and one endpoint in V, and every edge contribute degree 2. So it is contributing 1 degree to the vertices in U and 1 degree to the vertices on V. Therefore we see that sum of degree of vertices in U will come out to be sum of degree of vertices in V. So we see for 7 B is the right answer. Now this was the last question. Oh, okay, sorry. So what is the diameter of this? Yeah, what is the diameter of this graph?
2.
2. Yes, that's right. Because if you compute all these shortest distance, we'll see that maximum of them will be 2. Either two vertices are adjacent to each other, or they have a common neighbor. So yeah, so the answer is 2. Okay.
Ma'am, by
Yeah.
hello,
Yes.
ma'am, by seeing the diagram that we can say that the answer is 2, ma'am. But why that? What that statement refers to, ma'am? Let G be a graph whose vertices are the two-element subsets of a five-element set.
Oh,
How we can interpret with this diagram, ma'am?
Okay, yes, yes. So they are saying it is the two element subset of five element set and whose edge are pair of disjoint two element set. Okay, let me present my board, then I'll show you what they mean. Okay. Uh, Stop press. Yeah. So I think the screen is visible, right?
Yes, ma'am.
So the graph that they had drawn is this. Okay, this was the graph. It was a pentagon, and there was up inside there is also a pentagon. Okay, yeah. So this is bit similar to the high, so we have this. Okay, and yeah, yeah. Okay, so this was the graph. So they are saying it is two element subsets. Two element subset. So basically this is basically same as the qn case. So vertices are two element subsets of 1 2 3 4 5. Okay, so basically what are your vertices here? Their vertices are 1 2 2 3 4 5, all these sets like this. So and there is an edge if both are disjoint. So basically 1 2 is connected to 3 4 and 3 5 and 4 5. So vertices are basically two element subset of this first five natural number, and there is an edge between these two subset if they are disjoint. So in this case, suppose you take so you so this is 1 2. Now, yeah, so basically you have to figure out this. So suppose I'm taking this as 3 4 and this as uh, 3 5. And what is the other set which is disjoint? 4 5. Okay, now 4 5 is connect now 4 5 will be connected to, so basically you will be able to label these vertices like this. So now 4 5 will be connected to what all sets? It will be connected to 1 2. Basically you have to look at two element subsets whose intersection is empty. So 4 5 intersection 1 2 is empty. What are the other possibility? 1 3, and the other possibility is 2 3, right?
Yes, ma'am.
So basically you will be able to label all these vertices like in this fashion. Now you understand like what like the question.
Yes, ma'am. Yes, ma'am. Now I understand.
Yeah, so the
Thank you.
okay. Any other question?
No, thanks, miss. I'm leaving, miss. I have some work.
Yeah, okay, that's fine. So even time is up, so okay. So we'll meet next time. Now next, so this was this week's session which was supposed to happen on Sunday. So now next session will happen on 20 the Sunday after the coming Sunday, which will be 26th at same time 5 to 7 p.m. Okay, so see you next time.
Yes, ma'am. Ma'am, that